I'm like to try to talk about in an understandable way that our Brookhaven's this is local yet collaborative to the other university or even internationally. So many people in the many aspects are involved, and I want to talk the selected part of these large activities. So this is my talk. So this is we are using supercomputer and do something fundamental for particle and the nuclear physics. So this is my contents of my talk. After introduction and a semi-continuous introduction about the standard model of particle physics, this is a fundamental law of physics so far human beings know. And especially the part governing the strong dynamics or how the inter-subatomic physics is, the particles are behaving QCD, quantum chromodynamics. And then this theory or dynamics is very hard to solve. That's why we are utilizing supercomputer. And that's the name of method is lattice QCD. I'm going to talk about this very briefly, yet I hope sufficient. Then I move to the selected recent result of this lattice QCD. And sometimes I will talk about not only QCD, but including QCD plus QED. This is electromagnetism, quantum electrodynamics as well. This is new future. And then I summarize and mention about future prospect. So the mission in our collaboration is mainly focusing on the experiment. So we ourselves are theorists, but we try to make input, the large impact, and the large input, and get the interpretation of big experiments, such as RIC experiment or LHC, or many other experiments I'm going to talk about. To get the, so this is big endeavor, I don't have to tell you, but to get the what we really need, for example, big question such as what is a fundamental law of physics, or what is a fundamental particle there? Is there anything we don't know yet? So new physics. So those big questions, that's an ultimate answer we want to get. That's the reason why we are doing big experiment. And sometimes to interpret this experiment properly, you need help from theory. And especially subatomic physics, this is, as I'm going to tell you, this is very complicated and very peculiar, actually. So we need to kind of rip off or disentangle this strong interaction called QCD, subatomic dynamics, to interpret experiment and get a nice result or understanding. So as you know, so this is the molecule. This is kind of angstrom size. And you have a core called nucleus, and the electron are flying around in the quantum way. And about the 4 or 5 order of magnitude, this is 10 to the minus 15 or 10 to the minus 14 meter. We call this 10 to the minus 15 1 femtometer or 1 Fermi. This is the size, 10 Fermi or 1 Fermi is the size of this nucleus. So large nucleus is as large as 10-ish femtometer. And this further disentangled to smaller particle called proton or neutron, whose typical size is 1 femtometer. And so the core of atom is made of called two particles, two types of particles typically. One is proton, and this has an electric charge +1, and the other is neutron. This is neutral charge. And further, we know from 60s, both proton and neutron are made of further smaller particle called quarks. and these colorful particles. And there's label up UUD for proton and the neutron UDD. This is mentioning the flavor of quark, and U mentioned up quark, and D mentioned down quark, and this zigzag is mentioning very strong interaction binding these three quarks together. And this is actually another particle, or force carrier particle called gluon. And that's actors of this quantum chromodynamics, subatomic physics. And so far, the human beings, as far as human beings know, this is the most fundamental theory called standard model of particle physics. And there is an interaction, 4 of them. One is familiar electromagnetism. This is actually, in a sense, the unified to so-called weak interaction, which is responsible for example, nuclear reactor or beta decay, and also gravity. But my talk is mainly focused on this fourth or this first law interaction called strong dynamics, or QCD. And each interaction in modern physics, the interaction is, there is the force carrier. For electron, this is familiar photon, light. And weak interaction, this is so-called the weak bosons, W or Z bosons. And gravity, there's a graviton, supposed to be. And the strong dynamics case, the force carrier is called gluon, something gluing quarks. And the coupling strength in the unit of, let's say, strong dynamics is being 1 in a unit. Then electromagnetism that we are familiar with is 2 order of magnitude small, weaker. And it's actually the 6 of 1, 2, 3, 4, 5, 6. 6 order of smaller for weak interactions. And the gravity is further 40 digits down the road, so very weak. So usually the particle theory, the gravity is not playing a major role. And these interacting particles are quarks, typically, or charged particle for electromagnetism, and any mass or energy can do the gravity, while weak boson can interact for both quark and lepton. That's a interaction. And the particles, this is the particles, fundamental particles, elementary particles we know so far. So this circled red is major player in my talk. So this blue one, 6 of them is a quark, the 6 flavors of quark, 6 types of quark. So up, down, charm, strange, top, bottom. So 6 of them. And in the usual daily life, up and down are very playing a preeminent role, while the high energy physics experiment, these are playing major roles as well. And these are QCD, or strong dynamics force carrier gluon. This is electromagnetic force carrier photon, or gamma. And there's another familiar name, electron, that we always use in the daily life. And there's a very light, very weak interacting particle called neutrino of electron. And actually, there's a repetition of these quark and the lepton pairs in the 3 laws called 3 generation. And later I'm going to talk about this 2nd generation lepton, this sibling of electron called muon. But first, let me focus on this, how quarks are behaving in their nature. So quarks cannot be seen in experiment directly, at low temperature at least. And these are forming the bound particle. So several quarks, like 3 quarks or 2 quark anti-quark, 1 quark and 1 anti-quark, are bind to each other to make some bound state. And those are called hadrons. And when 3 quarks are bounded, this is called baryon. The proton or neutron I talked about is one of them, 2 of them. And this quark anti-quark bound state is called meson. These may not be familiar unless you're a particle physicist, or nuclear physicist, but the pion or kaon is a typical particle of this. And so let me, this is one page I'm trying to talk about what quantum, this strong subatomic dynamics is, quantum chromodynamics. This is very peculiar feature. There's a 2 or 3 outstanding feature. And that's primarily because of this is very strong dynamics. So as I said, force or interaction is carried by gluon, which is 100 times more stronger than electroweak. And because of this strength, apart from electromagnetism, where you have charge, then charged particle can emit photon, and the photon can absorb by another charge particle. That's how the charged particles are interacting with each other. Apart from this electromagnetism, the quark carries, instead of charge, electromagnetic charge, it's carried so-called color charge. So color, like red, green, blue, this is not really color you know. This is mathematical metaphor of this, how this interaction are governed, called SU3. And, but you can see, like in the charge, so let me do some. So like quark can change the color. So the formerly red quark emit some gluon of particular color combination, and they become blue. And this formerly blue become red. So that's how quark change the color and the interaction using this color charge. So in the QCD, quarks change the color, and this force carrier gluon is emitted or absorbed to give or get the momentum from quarks. That's how this strong dynamics occurs. And there's a many peculiar feature in this QCD. One of them, outstanding feature, is called confinement. So, like I said, no one can see the one quark in the low temperature. It's only the experimenter is only able to see this pair of baryon or meson. And this is because this color mathematics or dynamics is only able to exist. So this particle as a bound state, its white state or charge neutral state can exist in large, long distance or zero temperature. And this is called confinement. So there are only three. They can't be one quark, always three or one quark anti-quark. And the other outstanding feature of this is why nuclei exist. This is actually recent, the hot topic in the lattice QCD. This is also kind of a leaked force from gluon between proton or neutron or proton. There's a strong force interacting this so that the nuclei, the proton, can bound to each other in a very short distance, 10 femtometer length. And now the lattice QCD is able to compute these nucleon force. And so far, these are fundamental law. There's nothing the human being know that this is wrong. So this is supposed to be the theory of subatomic physics, every subatomic physics. And this is this wouldn't mean anything if you don't know this, but this is supposed to be Lagrangian or giving you the equation motion of quark and gluons. And if you can solve this equation, then you are supposed to know, in principle, everything in subatomic dynamics and almost, and very precisely. So that's a very nice feature of this elementary particle physics. So as I said, the gluon is very strongly interacting. So that's why you cannot solve this equation motion or dynamics by pencil and pen, while the electromagnetism, because it's 100 times weaker theory, you can use perturbation theory or Taylor expansion this is kind of pencil and pen without computer. You can use computer still, but you can do pencil and pen. That's the perturbation works for electromagnetism. But the QCD, the perturbation completely fails for many large set of problems. And that's why the lattice QCD calculation using supercomputer is proposed and used for last 40 years or so. So this is solving this dynamics, the equation motion numerically. And this is performing so-called Feynman's path integral in this formula on the computer, and to measure the quantum average of whatever you want in principle. There's several restrictions. So for example, you can measure how a proton is moving in the space or time by computing this quantum average. If you make this O, the observable makes protons operator or protons propagate, how proton is propagate. And these are coming from the equation motion of QCDs, this red part. And these are schematics of QCD. So first we discretize the space-time into mesh, 4-dimensional mesh. The 3-dimensional space and the 1-dimensional time, like this. And so this mesh, 4-dimensional mesh, this is a blow-up of mesh, and each vertex we put quarks, up-down strange quarks. And on the link we put gluons. So that this looks like quark emitting gluon or absorbing gluon by another quark. So this indeed describes this SU3 or color charge dynamics. And how large this mesh are? This is requirement from physics. So as I said, the typical size of proton is 1 Fermi. And you want to put a few, maybe let's say 5 proton into your lattice space-time. The real universe is very large, but 5 femtometer is what we can afford so far. And we know 5 femtometer is large enough. So 5 femtometer is this one extent. And also the size of one mesh, that spacing, the length between vertex, we set typically 0.1 femtometer or small to avoid systematic error coming from this discretization. So in the nature, this is smooth space-time. We make this more zigzag lattice so that we won't see the artificial effect of this discretization. We want to make this mesh smaller and smaller and take actually continuum limit. So the one number of site is about 50. It's 50. And so I'm changing 2 dimension. So the one mesh is 0.1 femtometer, and the length is 5 femtometer or so. This is only 5, but so one length is 50. And the space-time 4-dimensional, and there is other internal direction or colors degree of freedom. It's actually 100 million variables integration we are carrying out. So this is not one variable. This is actually 100 or 200 million, few hundred million variables integration. That's why we need a massive computer. So just to give the idea of how large the requirement of computing is. So just the typical, not very hard calculation, computing proton mass. This is needing order of 100 to 1,000 exa floating point operation. So floating point operation is either addition or multiplication or division or something like that. So you have to do this multiply out many times, and the exa is 10 to the 18. So you have to carry out 10 to the 20 or 10 to the 20 plus or minus multiplication just to calculate typical proton mass. And we are getting there. And this, in terms of the state-of-art computer, our Bruegel Q, this is not a very large installation. This is just one duct. We will see the picture next page, a few pages later. But it typically gets order of 100 days. And in terms of the computational, if you want to do this computing on your desktop, it will take order 100 or even 1,000 years to carry out, if it fits, this calculated proton mass. So that's the order of magnitude we are dealing with. And as a computational calculation or numerical calculation, there's many numerical calculations on the science community. Maybe this is better. The particular uniqueness of the lattice QCD calculation is, since this is first principle, because this is an elementary particle, there is no further basic known. So this has been, so once you know how to solve, your calculation result is useful for many, many long years. So in other words, this is stable numerical program. So people can invest a lot of resources or ideas for this calculation. That's maybe the uniqueness of the lattice QCD calculation I'm seeing. And Brookhaven is special in this lattice QCD theory because this very nice looking guy called Mike Kreutz. This is our high energy physics senior colleague. He actually came here and carried out the very fast lattice gauge simulation in end of 70s. So that's the starting of this field. Since then, Brookhaven make many breakthroughs, and has a huge impact on the lattice QCD community. I'm not going to dwell all the history, but the Brookhaven is particular historically has a very unique role on this lattice gauge theory, and there will be, I hope. Let me go to how we use supercomputer. Well, what is our supercomputer we use for lattice QCD? So this is massively parallel computer. So we have a small computing node. There's 16 cores, 16 computing unit in this size card. And we put 32 in this drawer size node card, drawer size. And this drawer we put into another 32 nodes in this rack, and this is this size. So in total, there is 1,024 computer card on one rack. And so typically, this is 200 teraflops. So 1 tera is 10 to the 12 operation in a second. This can do, on a peak, can do 200 teraflops. And we typically use, in the largest installation, we have a 1 to 10 petaflops machine. And at the Brookhaven, we have 0.7 petaflops. So it's not the very large installation, but it's very crucial and very useful for us to get a rapid calculation. And this is partly due to the large collaboration between Columbia and the Weekend and the University of Edinburgh, as well as IBM Watson Lab. And these are a picture of so-called interconnect. So not only massively large number of computing we need a rapid communication between these nodes in many directions. It's actually a 5-dimensional communication mesh. that's a secret, or that's a success recipe of these computers. And this is a history of year. So from 40s, the first ENIAC machine or something, to current state-of-art supercomputers. So this, and the x-axis is a peak speed of flops. So this is the, for example, 10 megaflops is this computer can do 10 to the 6 floating plus or addition or multiplication operation in a second. And in the, for example, 80s, where Microids started the computing, it's actually this machine, this CDC 7600, which has only 40 megaflops. And this was the use for fast gauge, lattice gauge calculation in end of 70s. I heard this was at the Brookhaven. And then going on, in around 96, we have first installation of a large QCD devoted machine called QCD-SP. This was 0.6 teraflops. And then 2005, QCD-OC, this was 20 teraflops. And now, a few years ago, a couple of years ago, we have 0.7 petaflops QCD-CQ installed. So as you can see, this is not very on top of the fastest at the year. But it's competing. It's close to the, this may have a gap, but this has a closer to competing capability to the state-of-art computer. And this computer and development of computer actually was possible by many collaboration of organizations. For example, the Columbia University has been very strong tie to us, and I did many computer development with us and IBM. And Research Center is providing a lot of human resources as well as computer resources for last 15 years. There's a US QCD, and also this Fritjof-Karsh et al.'s hot QCD. This is leak physics calculation on lattice, as well as the UK large, very strong collaboration centered at the University of Edinburgh and Southampton. These are collaboration. So we are not only using Brookhaven's local machine, but also US fastest computer like Titan or Argon's Mirror, as well as UK's installation or Japanese installation. And of course, these computers are useless without many good scientists, top-notch scientists. These are part of our collaboration, this RIKENBN Columbia and the UK QCD collaboration. And we are about order of 50 collaboration. And as I said, our local installation computer is not very fast. It's not the fastest computer at the time, but it's okay because we quickly develop the idea and explore idea, try and error, optimize parameter or optimize code. And before anyone else, we can use the national leadership computers such as Argon Mirror, or in Japan, Kobe's K computer, very efficiently. So that's our kind of business model. So we use local machine fully, so it's a very crucial ingredient for our activity. And once we are convinced this is a good idea or good code, we fully utilize the fastest computer by remotely. And that's actually many breakthroughs happen in this model. This is a little bit technical, but when it comes to computing, the algorithm or computational trick is important. This is what Lodi introduced when he introduced me, mentioned about this. This is what we come up in the name of all-mode averaging. So this is technical, but this is understandable. So let me try. It's actually, this is how you save computing. So it's something to do with saving. And actually, I think I get this very fast idea from my wife, who is very good at saving. And so you want to calculate something, some observable, maybe protons mass or something, protons propagate or something. Then you divide these protons into cheaper approximation, cheaper mimic, and the rest, so the difference between the cheaper approximation and the correct one. So this is cheap to calculate. This can be done quickly on computer. This is as long as original calculation. So this is expensive. Rest part is expensive. And we make this rest part kept and make this approximation part do many times. So since this is cheap, we can make this approximation a lot of time without spending a lot of computational time or money. And since we kept the difference or correction between exact, precise calculation and the cheap approximation part untouched, and do only this infrequently, and add together, and then the result you get is as good as original calculation. And this is true because of the symmetry that this system has. So what I'm plotting here is, this is Monte Carlo calculation. So you are averaging something. So this is samples, many samples have a fluctuation going up and down. This blue is your exact. And this dotted green is your cheap approximation. You can do cheap approximation. So there is a difference, but when it's up, it's up. The blue up, green up, blue down, green down. So this difference, the difference between exact and approximation has a flatter, lesser fluctuation. So even you do this calculation infrequently, the error, statistical error coming from this is small. While this green is still going up and down, has a large fluctuation, but it's okay because we do hero overload cheaply. So that's the simple idea, and I'm sure this is used in many times, but not on lattice so far, in this way particularly. And the bottom line of this is we can get at least 5 times faster, or sometimes 200 times faster computing without jeopardize or introducing bias. So we can get same, formerly 1 million machine, now worth 5 million or even 200 million machine. And this is now used in many, in US or in the world. So that's so I was talking about what is QCD we are solving and how we are solving, using what machine or what one trick we come up. Now I'd like to come to the selected recent result. The first is why the mass is emerged. This is origin of mass. This is complicated, so I'm not expecting everyone can understand this, but it's something to do with quark spin. The quark spin, there's 2 ways in the direction of momentum of the velocity of quark, or the right-handed or left-handed. When the quark is massless, this is flying speed of light. So you cannot go faster than speed of light. So you cannot change the right-handed rotation to left-handed rotation. So that makes the massless particle, the right hand and left hand can never mix or change from right-handed or upper spin to down spin. That's called chiral symmetry. On the other hand, if this chiral symmetry or mixing happening, then this introduces mass because this spin particle can go slower than light, speed of light. And this chiral symmetry is, or mixing, is kind of spontaneously happens in this strong dynamics, or QCD. What you are seeing is so-called the kind of energy density, or more precisely the topological or chiral charges. And you can see there's some ball shape, lamp shape thing turned on and off instantaneously, sometimes called instanton. And this is the source of effective mass of quarks. So quark itself has a very light quark, very small mass, but it's spontaneously acquire this effective mass by picking up this instantaneous breaking. And this phenomena, which is universal, invented by Nambu and Goldstone, Nambu has a Nobel Award in 2008 by that, is considered to be origin of mass. This is generally called the spontaneous breaking effect. And we could compute how large this blab is, or effect of this induced mass is, in the terms of quark-antiquark pair. And this is approximately a third of proton mass. So we can think effect of this quark pairs, or chiral condensation we called, is origin of mass. And this may be familiar with some of you, because this is exactly the mechanism that the Higgs particle, that origin of electron mass or lepton mass, for example, found in LHC, is acquire the mass. So instead of Higgs condensation in the QCD, we have quark condensation. And another prominent physical example of this spontaneous breaking is superconductor, or Landau-Ginzburg theory. And these are very complicated, and maybe you don't believe this, but we know what we are doing is right, because we now can compute many this hadron particle, baryon or meson, in first principle by inputting only 4 input, namely meson of pion, kaon, omega baryon. And these are converted in the standard model parameter of up-down quark mass or strange quark mass and coupling strength. And these are many particles, and these are B quark or D charmed particles. And we can compute, this is all the compilation of the worldwide effort. And as you can see, this black line, which is experiment, is nicely reproduced by lattice calculation. Some of them are prediction. So we are being convinced that this, what we are doing is very accurate, providing very accurate result. And next, I'd like to talk about why, this is kind of important, why proton is stable in this natural world. Because we have the sibling of proton, like I said in the beginning, neutral particle. And it happened to be that in the nature, neutron is 0.1% more heavier than proton, namely 1.2, 1.3 MeV heavier. And now this Heisenberg in 32, he was advocating there is the symmetry, or there is a resemblance between proton and neutron. And this can be understood if the up-type particle, up-type quark and down-type quark are exactly the same. Then you can exchange up and down, then that means this neutron up, down, down to up, up, down. So this is exactly the same particle. But in nature, there's a two difference between up quark and down quark. One is the D quark, down quark is slightly 50%, not slightly, 50% heavier than up quark. That's a mass difference. Also, the up-type quark has 2/3 charge, down-type quark has -1/3 charge, so electric charge are different. So by doing the QED, electromagnetism intact with QCD, now the lattice community are able to predict or compute this very 0.1%, very small mass difference. And this is the latest result from BMW, German-based collaboration, and they have very nice agreement. And they can even divide this mass difference, original mass difference, that from the quark mass difference and QED effect. So actually QED effect has a negative effect. So it's actually making proton heavier. So that was the mass. So I was talking about hadron mass and also proton-neutron mass difference. Now getting more subtle, almost more precise region, namely quark flavor physics. So we have, as I said, we have 6 types of flavor of quarks. Use this. 6 types of quarks. And this quark, by emitting, for example, up quark can emit W boson, electroweak force carrier, and coming to down quark, or strange quark, or bottom quark. So these down type quarks. And each time it's changed to the other down type quark, this has the probability amplitude, which is whose theory is constructed with these 3 gentlemen, Kabibo, Kobayashi, Masukawa. Latter 2 got a Nobel Prize in 2008 due to this work. And this probability amplitude, Kobayashi Masukawa matrix element, for example, amplitude up to down is VUD, strange VUS, bottom VUB. So these are amplitude which up quark can convert it into each of down type quark. And because total probability of up being to 1 of 3 quark need to be 1, so we can constrain if our understanding of this flavor, like unlike we have a 4th generation, other unknown quark exist. Unless these things happening, new physics is happening, we can say the total probability being 1. This is quantum theory, so it's absolute value square. And this is called CKM unitarity condition. And this is actually a very nice check on standard model, and very precise check. This, for example, the pion leptonic decay. So pi meson particle into muon or kaon, this is up strange particle. Pion is up-down particle, can emit W and emitting muon or neutrino. Each time this is doing this, the Kobayashi Masukawa matrix, flavor changing matrix, is multiplied. And from the how large this decay width or decay amplitude is from experiments, something like this is pion into mu meson, and also this how quarks, the U quark and down quark, collide each other, this probability you can calculate on lattice very precisely, sub% now. And these are experimentalist input between these decay widths. So it's also 0.5%-ish accuracy. And you get this FKO by F pi, this dynamics factor, 0.5%, so you can get this Kobayashi Masukawa matrix, what you want, in sub%. And you can do similar game for another similar process, K to pi, semi-leptonic decay, like this, K emitting strange to U and lepton pairs. And this also do lattice and experiment constraint to get VUD. And the probability of total probability preservation that Kobayashi Masukawa predict is very nicely realized. Look at this, the 4-digit 9. This is almost latest result. And these are the VUS, VUD plane from this leptonic decay as well as the this semi-leptonic decay. So it's everything makes sense. So all 3 lines are within very small deviation, it fit. So there seems to be not too much room for unknown physics so far. Maybe this must be heavy. So that's one of the examples how this lattice calculation interplay with lattice calculation and the precise experimental data work together to get the stringent check of standard model, or if there's something wrong happening, that's very exciting because that would mean we are finding something. And that's actually the last topic I want to talk. This is the Brookhaven's, I'm running out of time, but let me quick here. This is Brookhaven's very prominent experiment until 2004. You might know this. So muon is sibling of lepton, has a spin like quark. And if the spin is along the external, so you put the magnetic field B, and if the spin's direction is along with B or anti the other side of spin, then the energy difference is could be occurred. And this is magnetic moment mu. And this magnetic moment mu of muon, if there is no quantum effect, like this is B, the photons, this photon, the zigzag is supposed to be from this external magnetic field. And if there is no quantum effect, this is lepton, then this magnetic moment is exactly in the unit of magneton 2. But there is quantum correction. For example, virtual photon can emit and absorbed by lepton. That makes this Landes G factor deviate from 2. And so you can get all the quantum correction, not only photon, but actually hadrons, which is something to do with gluon. And if you can precisely measure, which Brookhaven's experimentalists have done, you can directly compare theoretical understanding and the experimental result. And these are theoretical understanding. So from the dawn of QED, they have been doing this QED correction till 2012. Now they have 10th order perturbation. This is very heroic theoretical calculation. And now this QED part, which is largest contribution, that uncertainty is very small. And the largest uncertainty, interestingly, is hadron. So this is where lattice can help, lattice QCD can help. And this is actually two types of hadronic contribution in the muon's anomalous magnetic moment, and this second one called hadronic light by light. So this external magnet emitting quark and anti-quark and emitting 3 photons. So it looks like photon is scattering each other, so it's light by light. This light by light diagram has one of largest, and it's actually theoretically less checked contribution, and which we are carrying out for the first time. But Brookhaven's, before going that, Brookhaven's experiment until 2004, look at this quote. There's a 9-digit. So this is one of the most precisely measured quantity by scientists. And it's actually half of per million accuracy they quote. So no wonder you can see this, not only photons quantum correction, but hadrons quantum correction. And now many of you might know this Brookhaven's muon ring is sent to Fermilab, Chicago, Illinois. And they are planning to do this 0.5 ppm accuracy down to 4 times smaller, and plan to data take from 2016. And so, currently the direct comparison, this is by our colleague Marciano, the experiment of Brookhaven and the standard model prediction has a deviation. So it's not everything is understood, I think. So it's like, it might be some calculations mistake, like the hadronic uncertainty is underestimated, that might be possible, or more excitingly, this might be sign of something new hidden in this. And so it's definitely worth look at this deviation. So what you're looking at is this Brookhaven's result of G-2, and the theoretical result, there's a 3-point sigma difference. And if central value won't be changing, and Fermilab can reduce this error bar into 4 times smaller, this is definitely the discovery of something new. So that's why we need to work hard on lattice to carry out this hadronic contribution, especially light by light. And we recently have the first breakthrough calculation on this. I don't have time to do this because I'm running out of time. So this is summary. I hope I give you some sense of what our activity is. This is very large activity involving many people, many ideas, many top-notch young scientists. And one of goal is providing precise theoretical calculation for precise experiment. And that makes the either standard model checked or discover new physics. And we go to some example of results such as mass or origin of proton stability by QED, QCD, or quark flavor. And now we are vigorously working on near future, hopefully, new breakthroughs, such as, like I said, muons, hadron vacuum polarization, or hadron light-by-light effect in what experiment is required 1% and 10% accuracy. This is very urgent and timely matter, as well as the, maybe Lori said, this more than 50 years homework for theory, K2 pi epsilon prime over epsilon, which we got the award. This is something to do with matter-antimatter difference. This is very exciting. We are about to get the final result, I believe. As well as the more important, another important nuclear structure, it's nuclear physics, something to do with EIC or so on. And so stay tuned, please. Thank you very much.
We have time for a few questions.
Yeah, one question. On the whole mode average, how do you know which is the ones to pay attention to and which ones to not sample so much?
So Lori asked about all mode averaging. How do I know which is to repeat and which is not? For each of sample, we do cheaper calculation and expensive calculation. And for each sample, we only repeat the cheaper one. So whatever cheap one, and as far as this cheaper one is semi-good approximation, we repeat. And we know by doing this, we can improve the statistics. Is that answer to your? So we are not cherry picking, if that's what, yeah.
So the blue gene architecture is designed for nearest neighbor
Yes.
calculations, which is very good for QCD, and on the other hand, Titan is not. How much does that get you in the performance and the efficiency?
Titan, yeah, I personally don't know if someone can answer. I will be happy to. I believe generally the peak 10% of peak is the typical figure. Titan.
And for the
Blue gene, I think they are in the good condition, like if the size is optimal. I think it's roughly 20, give or take 5%, 20%. So I think it's nowadays many cores age. This is good number, I suppose.
So my question, coming from quite a far away out of the field, is how do you know your calculations are done when they're done? You get a little text message that says it's been 100 days?
So we monitor the intermediate result, and if the error, not only statistical error but the systematic error, are going down beyond necessary, which is set by experimentalists, then we are done. That's how we are.
And you have to compete for your access to the computers with the general scientific community, so you choose carefully which calculations to run.
Right. The prioritize is very hard but important.
And do you do that by yourself or in a committee with people? Or?
So we have the local machine. We have full control. I mean, within collaboration, we discuss and prioritize. And the external resources we apply for CPU machines, and their allocation committees will allocate and prioritize accordingly.
Maybe this is how they chose between Titan and Blue Gene,
QCD generally especially our special quark called domain wall, which are developed by Sony et al. Is optimal on Blue Gene series rather than the cluster.
So in your most recent calculation, what is the ion mass that
We are doing the physical pion, which is 135 MeV. Yeah, we have on physics 2 lattice spacing, so this is very exciting stage for us. The final dream is coming close.
So if there's no further questions, there should be refreshments in the lobby, and let's thank our speaker one more time.
Thank you very much.